In this module, we will look at the navigation systems installed on the ATR. We will first go over an overview of the aircraft's navigation systems. Following that introduction, we will examine the VOR ILS system, the marker beacon system, the DME, the ADF, and the radio altimeter systems. Next, we will look at the enhanced ground proximity warning system and the weather radar. Since some ATR 42500s have an optional GPS system, we will look at that system as well. The ATR includes all the navigation systems found on other modern aircraft. These navigation systems consist of a dual VOR navigation system, a dual ILS system, a single or dual DME system, a dual automatic direction finder system, a single marker beacon system, a single radio altimeter system, an enhanced ground proximity warning system, a single color weather radar system, and an optional single global positioning system. The navigation system uses numerous antennas that are mounted on various locations of the exterior of the aircraft. Navigation information feeds audio signals to the remote control audio unit so that the crew may identify and verify station identifiers. The remote control audio unit is the central processor of audio signals from all the cockpit electronics. There is a separate processor for each crew member which controls audio based on what the crew selects on their individual panel. There are different channels of output for headsets, loudspeakers, etc. In addition, the navigation systems supply system information to the symbol generator units for processing. The SGUs use this signal to display system status information on the electronic attitude director indicators and the electronic horizontal situation indicators. There are two independent VOR receivers installed on the aircraft. VOR-1 is powered by the DC standby bus, and VOR-2 is powered by DC bus 2. The two VOR receivers use the same VOR antenna, which is located on the vertical stabilizer. The VOR receivers are controlled by their associated nav control boxes, which are located on the left and right sides of the glare shield. The audio signal from each VOR receiver is fed to the remote control audio unit to enable the crew to listen to the audio signal and station identifier. The remote control audio unit is covered in the communications module. The VOR receivers also supply station signal information to the associated symbol generator unit. In turn, each SGU displays VOR information on the associated electronic horizontal situation indicator. In addition, VOR information can also be displayed on the RMIs. A transfer system enables each crew member to select the opposite VOR receiver to drive the deviation bars on the associated EHSI. This switching is controlled by the captain switching or first officer switching panel on each crew member's respective side. For the captain to use the first officer's VOR or localizer receiver, press the VOR ILS push button on the captain switching panel. Captain 2 will illuminate on the first officer's button. For the first officer to use the captain's VOR or localizer receiver, press the VOR ILS button on the first officer's switching panel. First officer 1 will illuminate on the captain's button. Each crew member can select a desired VOR course to fly. The course is selected by rotating the associated course knob. The selected course is then displayed on the associated EHSI. The aircraft is equipped with two ILS receivers. The ILS receivers are incorporated in the same box as the VOR and therefore use the same power source. The ILS receivers are independent of each other. However, they share the same localizer and glide slope antennas. The localizer antenna is actually the same antenna used by the VOR system. The common ILS glide slope antenna is located on the bottom of the fuselage, just aft of the radome. The ILS receivers are controlled by the same navigation control panel used by the VOR receivers. The control panel switches from VOR to ILS and vice versa based on the frequency that is dialed in. The ILS receivers supply audio signal information to the remote control audio unit and the associated symbol generator unit. ILS information can be used to drive the deviation bars on the opposite side. The transfer system uses the same source switches described earlier in the VOR section of this module. The VOR and ILS receivers are controlled by an associated nav control box located on either side of the glare shield. This control box is used to select radio frequencies for either navigation source. The captain's receiver is navigation source 1 and the first officer's is navigation source 2. However, both RMIs receive signals from both radios, so either pilot's RMI can show pointers for both VOR or localizer 1 and 2. The left knob consists of an inner and an outer knob. The outer knob is used to turn the associated VOR and ILS receivers on or off. The hold position enables the crew to select a different receiver frequency while holding the DME receiver to the current frequency. In effect, this allows the crew to display VOR or ILS information from one station and DME information from a different station. Normally, the switching of the VOR or ILS frequency will also tune the DME receiver to the DME station attached to the new VOR or ILS frequency. To use the hold function, you tune the frequency you want to hold and then select the hold position. DME will then stay on the tuned frequency no matter what else is tuned in. The inner knob is used to adjust the volume of the audio signal of the selected frequency. The frequency display window shows the active frequency in the upper portion of the display. The standby frequency is displayed under the active frequency. Frequencies are selected by the dual frequency select knob. This knob consists of an outer knob and an inner knob. The outer knob changes the leftmost 3 digits of the frequency, whereas the inner knob changes the 2 rightmost digits. The selected frequency is displayed in the lower part of the frequency window. The active and standby frequencies are switched by means of the transfer memory switch. This toggle switch is spring-loaded to the neutral position. It works like a standard flip-flop switch. Placing the toggle switch to the transfer position swaps the 2 frequencies in the frequency display window. The frequency in the lower portion of the frequency display window becomes the active frequency and is displayed in the upper side of the frequency window. Conversely, the previously active frequency now becomes the standby frequency and is displayed in the lower window. Repeatedly placing the frequency transfer switch to the transfer position will swap the frequencies back and forth. The memory position of the transfer switch is used to select a stored frequency. Each time the switch is placed in the memory position, the next stored memory is displayed in the lower portion of the frequency display window. Up to 4 frequencies can be stored in memory, so you can theoretically cycle through 4 different stored frequencies. A frequency is stored by selecting a frequency which is displayed in the lower portion of the frequency display window. When the Store button is pressed, the upper window will display an available storage memory slot. Once the slot number is displayed, you have 5 seconds to store the selected frequency in the selected slot by pressing the Store button a second time. During this 5-second period, a different memory slot can be selected by placing the transfer memory switch in the memory position. After 5 seconds, the navigation control box returns to its normal function. The frequency select knobs can be used to directly change the active frequency without the need to pre-select it and transfer it. This direct mode is entered by pressing and holding the active button for 2 seconds. After 2 seconds, The bottom portion of the frequency display window displays dashes, and the frequency select knobs are then used to change the active frequency. The navigation control box is returned to the normal mode of operation by pressing the active button a second time. The nav control box remotely sets the frequency of the associated VOR and ILS receivers. In the event the actual receiver frequency is different from the selected active frequency, the active light on the left side of the frequency display window will flash. 3 text annunciator lights are located below the frequency display window. The possible annunciations are memory, remote, and hold. The memory light illuminates when a frequency that is stored in memory is displayed in the lower portion of the frequency display window. The remote light illuminates when the navigation radio is controlled by a different system, such as the flight management system. The hold light illuminates any time a DME frequency is being held. In this situation, the upper part of the frequency display window shows the active frequency, and the lower part shows the DME frequency that is being held. The test button is used to initiate a self-diagnostic test. Malfunctions are indicated by a diagnostic code displayed on the top line of the frequency window. A light sensor in the faceplate of the navigation control box automatically adjusts the brightness of the navigation control box display. The ATR has 2 marker beacon receivers. Although independent of each other, the 2 marker beacon receivers share the same marker beacon antenna that is located on the bottom side of the fuselage, just forward of the main landing gear bays. The marker beacon radios are controlled by the associated navigation control box. The marker beacons are integral components of the VOR-ILS receivers. They are on any time the related VOR-ILS receiver is on. Marker beacon signals are supplied to the associated symbol generator. Only Marker Beacon System 1 audio signals are supplied to the Remote Control Audio Unit and the Flight Data Acquisition Unit. The marker beacon receivers are designed to receive marker signals from the outer, middle, and inner airway markers of an ILS approach. Station passage is indicated by an audio signal and an indication on the electronic attitude director indicators. The sensitivity of the marker beacon system can be adjusted by the marker switch located on the captain's lateral panel. The sensitivity of the receivers can be adjusted to high or low. On King installations, the marker switch also has a test function. The ATR is equipped with a distance measuring equipment system. Some aircraft have an optional second DME receiver. The DME measures the slant range from the aircraft to the DME station. The DME receiver is controlled by the NAV1 control box. If a second DME is installed, it is controlled by the NAV2 control box. The DME receivers are powered by the associated DC bus. Unlike the ILS and VOR receivers, each DME receiver has its own dedicated DME receiver antenna. These antennas are located under the forward part of the fuselage. DME frequencies are automatically selected as a function of the ILS or VOR frequency that is selected on the nav control boxes. When you change an ILS or VOR frequency, the DME will change as well. The DME receivers supply information to the associated remote control audio unit and the associated symbol generator. In turn, the symbol generator indicates DME distance on the EHSI. As discussed previously, a DME frequency can be held. In this case, a change in a VOR or ILS frequency will not cause the DME receiver frequency to change, but instead remain locked to the previously selected DME frequency. A held DME frequency is indicated by an amber H on the upper right-hand side of the EHSIs. A single automatic direction finder receiver is part of the aircraft's navigation equipment. The ADF system uses a single ADF antenna that is located on the top of the fuselage. Some aircraft have an optional second ADF receiver. The ADF receiver is powered by the DC standby bus. If a second ADF system is installed, it is then powered by DC bus 2. ADF bearing information drives the bearing information on the EHSI through the associated symbol generator unit. The ADF bearing information is also displayed on the RMIs. ADF audio signals are also fed to the remote control audio unit. This allows the crew to identify and monitor the ADF station. The ADF receiver is controlled by an associated ADF control box located on the center pedestal. If the aircraft is equipped with an additional ADF receiver, then that receiver is controlled by an associated ADF control box as well. The ADF receiver control box is similar to the navigation receiver control box with a few exceptions. The power, mode, and control volume knob is a 4-position rotary knob that is used to depower the ADF system or to select the desired mode of operation. The test button initiates a test of the ADF system. Malfunctions are indicated by a diagnostic code displayed on the top line of the frequency window. Like the Collins nav control boxes, the ADF control box has a memory and a remote annunciator. The memory annunciator illuminates when a stored memory is displayed in the standby frequency window. The remote annunciator illuminates when the ADF control box is controlled by another system, such as the flight management system. The aircraft is equipped with a radio altimeter, which provides an indication of the aircraft's height above the ground when the aircraft is below 2,500 feet AGL. The radio altimeter consists of a single transceiver and 2 radio altimeter antennas. The 2 radio altimeter antennas are located on the bottom part of the fuselage, forward of the landing gear bays. Height is determined by reflecting radar signals off the terrain. The system uses the leading edge of the reflected radar wave to figure out the aircraft's height above the ground. The radio altimeter is integrated with various other systems for terrain proximity alerting. It is powered by DC bus 1. The radio altimeter reading is displayed on the bottom right-hand side of both electronic attitude director indicators. The display can indicate altitudes between -20 feet to 2,500 feet. The radio altimeter display is not visible when the aircraft is above 2,500 feet AGL. Below that altitude, the display will indicate the aircraft altitude above the ground. If the radio altimeter data is invalid, the radio altimeter displays will indicate amber dashes. To comply with airworthiness regulations, most ATR fleets are equipped with an Enhanced Ground Proximity Warning System, or EGPWS. The EGPWS includes the Terrain Awareness Alerting and Display function, as well as the Basic Ground Proximity Warning System, or GPWS, functions modes 1 through 6.
Because the overwhelming majority of controlled flight into terrain, or CFIT accidents, occur near an airport, and the fact that aircraft operate in close proximity to terrain near an airport, the terrain database contains higher resolution grids for airport areas. Lower resolution grids are used outside airport areas, where aircraft en route altitude makes CFIT accidents less likely, and terrain feature detail is less important to the flight crew. With the use of accurate GPS or FMS information, the EGPWS is provided present position, track, and ground speed. With this information, the EGPWS is able to present a graphical plan view of the aircraft relative to the terrain and advise the flight crew of potential conflict with the terrain or obstacle. Conflicts are recognized and alerts provided when terrain violates specific computed envelope boundaries on the projected flight path of the aircraft. Alerts are provided in the form of visual light enunciation of a caution or warning, audio enunciation based on the type of conflict, and color-enhanced visual display of the terrain or obstacle relative to the forward look of the aircraft. The terrain display is provided on the weather radar indicator, EFIS display, or a dedicated EGPWS display, and may or may not be displayed automatically.
The EGPWS uses internal terrain, obstacles, and airport databases to predict a potential conflict between the aircraft's flight path and terrain or obstacles. Terrain or obstacle conflict results in the EGPWS providing a visual terrain mode that is automatically displayed on the EHSI, as well as audio warnings or caution alerts. Loss of the terrain awareness function will not affect the operation of GPWS functions, provided that the input signals necessary for GPWS operations are still available. If radio altitude information is present, the warning system will function normally. With the geometric altitude function, the EGPWS can operate reliably throughout extreme local pressure and temperature variations. The EGPWS is not susceptible to misset altimeters by flight crew and does not require any custom input or special procedures by the flight crew when operating on QFE. EGPWS equipment has a forward-looking capability so that an early warning will be given if the airplane is approaching sharply rising terrain. Alerts and warnings in modes 1 and 2 are only given when the airplane is less than 2,450 feet above the local terrain. Mode 1 is excessive sink rate. Mode 2 is for excessive terrain closure rate. If no corrective action is taken, a maximum of 30 seconds will elapse between initial receipt of the alert warning and contact with the ground, and this will be lessened if the rate of descent is excessive or there is rising ground beneath the airplane. Navigation must not be predicated upon the use of the terrain obstacle awareness display. The GPWS will provide little, if any, warning for a normal stabilized descent in landing configuration into level terrain, where there is no operating glide slope or where the minimum alert feature has not been utilized. All modes are inactive below 50 feet AGL in order to avoid nuisance warnings caused by ground effect-induced static pressure fluctuations. In addition, all modes are inactive above 2,450 feet AGL, which represents the altitude cutoff limit to eliminate nuisance warnings at en route altitudes. Unwanted warnings, also called false or nuisance warnings, may be received during normal safe operations. An example would be when the airplane is being vectored by ATC and is descending into an area of hilly terrain. A Mode 5 glide slope alert may be triggered when the airplane is being flown outside the validity area of the glide slope signal, such as when maneuvering visually to land on a non-instrument runway following an approach to the ILS runway. This alert can be silenced by depressing the GPWS glide slope switch on the side of each pilot's forward panel. This is a push-button switch which illuminates either GPWS or glide slope. GPWS eliminates for modes 1 through 4, and glide slope eliminates for mode 5. An alert warning will also be triggered if the approach is flown with the flaps set to a different position from that normally used for landing. This is the mode 4 condition. To avoid receiving unwanted alerts, the terrain awareness alerting and display function must be inhibited. This is done by selecting the terrain inhibit switch when within 15 nautical miles of takeoff, approach, or landing at an airport not contained in the EGPWS airport database. The terrain display can be selected manually using the Display Select push button. This button will illuminate terrain in blue when the terrain display is selected on, or radar in blue when the weather radar display is selected on. The EGPWS will automatically present a terrain display on the weather radar portion of the electronic horizontal situation indicator during a terrain event. This is purely an EGPWS feature, not a GPWS feature. The terrain inhibit switch overrides all terrain functions, including the automatic display on the weather radar. When this is selected, only the standard GPWS functions are available. Terrain alerts are depicted by the color yellow or red. Terrain is not shown if it is more than 2,000 feet below the reference altitude. Terrain is not shown if terrain elevation is within 400 feet of the runway elevation nearest to the aircraft. The EGPWS has an Integral Global Positioning System, or GPS. It does not require an airport ID. For the first flight of the day, the system should be tested by pressing the GPWS glide slope push button. In the event of an engine failure followed by an emergency turn procedure, the EGPWS may activate but must be ignored. This occurs because the limits defined in the terrain function of the EGPWS are greater than those specified for an emergency turn procedure. Certain limitations are applicable to the EGPWS. First of all, navigation is not predicated on the use of the terrain awareness display. The EGPWS database, displays, and alerting algorithms currently do not account for man-made obstructions. Pilots are authorized to deviate from their current ATC clearance to the extent necessary to comply with an EGPWS warning. And finally, the terrain display is intended to be used as a situational tool only and may not provide the accuracy and/or fidelity on which to solely base terrain avoidance maneuvering. Audio warnings vary in urgency or loudness depending on the degree of hazard. Pull up, for example, is always loud and urgent. The EGPWS terrain inhibit switch is installed on the captain's side panel. The EGPWS terrain inhibit switch is also used during approach mode in airports not covered by the EGPWS database. The EGPWS terrain inhibit switch assures protection against unwanted terrain alerts, inhibits the terrain mode operation, and, if actuated, the caution message "Terrain inoperative" is displayed on the weather radar display. The terrain function is to be inhibited if within 15 nautical miles of takeoff, approach, or landing at an airport where any of the following conditions apply. The airport has no approved instrument approach procedure, the longest runway is less than 3,510 feet in length, the airport is not included in the Allied Signal Database. A system test is achieved by pressing the GPWS glide slope push button and checking that the following occur in succession. Both the GPWS and terrain fault lights illuminate. The GPWS fault light illuminates on the crew alerting panel. Both amber glide slope lights illuminate. The oral glide slope alert sounds. Both amber glide slope lights extinguish. Both red GPWS lights illuminate. The pull-up oral alert sounds. Both red GPWS lights extinguish and then illuminate a second time. The blue terrain lights on the display select push button illuminate on both panels. A terrain test pattern is displayed on each EHSI. The terrain ahead pull-up oral alert sounds, and both red GPWS lights extinguish. After 12 seconds, the terrain display test pattern is removed, the GPWS and terrain fault lights extinguish, and the GPWS fault light extinguishes on the crew alerting panel. The EGPWS provides the basic GPWS alerting in 6 modes. Each mode is predicated upon an envelope based on aircraft position relative to the terrain. The size of the envelope is determined by different factors such as aircraft speed, altitude, and configuration. These modes are referred to as modes 1 through 6. Mode 1 alerts are generated when the descent rate is excessive while the aircraft is close to the ground. If the aircraft's descent rate within 2,500 feet of the ground exceeds a certain value, the EGPWS issues an oral sink rate warning and the GPWS light illuminates red.
Mode 1 alerts flight crews to excessive rates of descent when the aircraft is near terrain. Using radar altitude and rate of descent information, The ground proximity warning computer monitors the flight profile when an aircraft is within 2,500 feet of terrain. Should an excessive rate of descent develop for the aircraft's current altitude above ground level, the red GPWS warning lamp will illuminate and the voice alert sink rate will be heard.
Sink rate. Sink rate.
If the rate of descent continues or worsens, a continuous pull-up voice warning will be heard.
Pull up. Pull up. Pull up.
As the aircraft recovers from the excessive rate of descent, the red GPWS warning lamp will extinguish and the voice warning will cease.
If the descent rate increases, the EGPWS will announce pull up and the GPWS light illuminates red. This warning will continue until the aircraft's descent rate is corrected. Mode 2 alerts are issued when the terrain closure rate is excessive. This would occur when the terrain is rising rapidly.
Mode 2 warns flight crews of excessive closure rates with rapidly rising terrain. Using airspeed, rate of descent, and radar altitude, GPWS compares terrain below the aircraft to the flight path. If terrain rises significantly within 2,000 feet of the aircraft, a closure rate is measured. When the closure rate shows danger to the aircraft, the red GPWS warning lamp will illuminate, and the voice alert terrain will be heard. If the closure rate continues or worsens, the voice call-out will change to a continuous pull-up warning until terrain is no longer a threat.
Terrain, 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 terrain. Pull up.
To help ensure sufficient recovery, the red GPWS warning lamp will remain illuminated until the aircraft climbs 300 feet above the altitude where the last pull-up voice warning was heard.
Mode 2 alerts are not dependent on the aircraft descending, in level flight, or climbing towards rapidly rising terrain. The EGPWS uses the radio altimeter, vertical speed information, and the terrain database to issue Mode 2 warnings. Mode 2 actually consists of two submodes, 2A and 2B. Mode 2B is enabled when the flaps are selected for landing, the aircraft is on an ILS approach and is within 2 dots of the localizer center line and glide slope path, and during the first 60 seconds after takeoff. Under these conditions, the EGPWS will issue an oral terrain warning when the terrain closure rate exceeds a certain value. In addition, the GPWS light illuminates red. If the closure rate is not corrected, the EGPWS will eventually issue an oral pull-up warning and the GPWS light illuminates red. The oral warning is repeated until the aircraft's closure rate is reduced. Closure rate is reduced. Mode 2A is enabled when the conditions for Mode 2B are not satisfied. The EGPWS issues an oral terrain caution when the terrain closure rate is excessive. In addition, the GPWS light illuminates red. If the closure rate is not corrected, the EGPWS will eventually issue an oral pull-up warning. The warnings will continue until the closure rate is corrected. During the correction, the pull-up oral warning will be replaced with the terrain oral caution. The terrain oral alert sounds until the aircraft climbs at least 300 feet, or when the radio altitude exceeds the detection range of the radio altimeter. Mode 3 provides warnings when there is a significant altitude loss after takeoff or during a go-around. In the event of an altitude loss after takeoff or go-around, the EGPWS will issue an oral don't sink caution message and the GPWS light illuminates red.
Mode 3 warns flight crews of inadvertent descents and loss of altitude after takeoff or during a missed approach. GPWS recognizes a takeoff or missed approach using aircraft speed, radar altitude, barometric altitude, and aircraft configuration changes. GPWS then monitors radar altitude and barometric altitude during the initial climb-out. Should the aircraft descend, GPWS compares any loss of baro altitude to peak altitude gained. When this difference is roughly 10%, the red GPWS warning lamp will illuminate and the voice alert "Don't sink" will be heard.
Don't sink. Don't sink. Don't sink.
When a positive rate of climb is
sink.
re-established, the red GPWS warning lamp will extinguish and the voice alert will cease. Once the aircraft has attained 1,000 feet above ground, Mode 3 is disabled. When GPWS again detects a takeoff or missed approach situation, Mode 3 protection is automatically re-enabled.
The GPWS light will not extinguish until a positive rate of climb is established. Mode 3 is disabled when the aircraft has gained sufficient altitude and is no longer in the takeoff or go-around mode. It is active between 75 and 1,500 feet after takeoff. Mode 4 provides unsafe terrain clearance alerts and warnings during climb, cruise, initial descent, or approach.
Mode 4 provides minimum terrain clearance protection in all phases of flight. GPWS will alert the flight crew to insufficient terrain clearance based on airspeed, altitude, rate of descent, and aircraft configuration. Mode 4 protection is especially valuable when the aircraft is on a normal flight path, where excessive descents or closure with terrain are not a factor. To understand the scope of Mode 4 alerts, let's follow a typical flight from takeoff to touchdown. As shown a few moments ago, Mode 3 protection is automatically enabled as the takeoff occurs. At the same time, Mode 4 begins to build a floor below the aircraft during climb-out. This floor will continue to build under the aircraft until reaching roughly 800 feet above ground, where it will remain throughout the flight until the aircraft begins initial approach at the destination. If the aircraft penetrates this floor during the flight, the red GPWS warning lamp will illuminate and the voice alert "Too low terrain" will be heard.
Too low terrain. Too low terrain.
Once the aircraft is safely back above the protective floor, the red warning lamp will extinguish and the voice alert will cease. During the approach and landing, GPWS monitors airspeed and aircraft configuration. The minimum terrain clearance floor is automatically adjusted as airspeed is decreased. If landing gear is not down and locked at 500 feet above ground, the red GPWS warning lamp will illuminate and the voice alert "Too low gear" will be heard.
Too low gear. Too low gear.
If flaps are not set to landing configuration by 170 to 250 feet, the red GPWS warning lamp will illuminate and the voice alert "Too low flaps" will be heard.
Too low flaps. Too low flaps.
Pilots may elect to disable the flap alerts by engaging the flap override function either prior to or during a flap alert enunciation. This allows landings in configurations other than normal landing flaps with no GPWS.
The eGPWS uses the radio altimeter and the aircraft's position in relation to the terrain database. Mode 4 actually consists of 3 submodes. Submode 4A provides alerts to prevent a gear-up landing. Submode 4A is active once the aircraft reaches 700 feet AGL after takeoff. The standard upper boundary for Submode 4A is 1,000 feet. A "too low gear" oral alert sounds if the aircraft descends below 500 feet AGL and the gear is retracted. In addition, the GPWS light illuminates red. The upper boundary increases with airspeeds above 190 knots to provide an increased alert time. Above this speed, the eGPWS will issue a "too low terrain" alert if the aircraft penetrates the boundary and the gear is retracted. Submode 4B is activated when the aircraft is on approach with the landing gear extended and the flaps are not in the landing configuration. The boundary for Submode 4B is 1,000 feet. The red GPWS light illuminates and the oral too low terrain is announced if the aircraft penetrates this boundary with the gear down, but the flaps are not in the landing configuration. The boundary decreases to 245 feet radio altitude when the aircraft speed is less than 159 knots. If the aircraft penetrates this boundary when the gear is down and the flaps are not in the landing configuration, the EGPWS will issue an oral too low flaps alert. In addition, the GPWS light illuminates red. The oral and visual alerts will continue until the flaps are placed in the landing position. The too low gear warnings take precedence over the too low flaps warnings. In the event of an abnormal flap position, the sub-mode 4B too low flap oral warning can be disabled by the flap override position of the GPWS selector switch on the captain's side console. Sub-mode 4C provides alerts in the event the terrain is rising faster than the aircraft is climbing. Sub-mode 4C alerts consist of an oral too low terrain warning and an illuminated GPWS light. Sub-mode 4C is active after takeoff or go-around at radio altitudes above 245 feet when the landing gear and flaps are not in the landing configuration. Mode 5 provides below glide slope deviation alerts when the aircraft has penetrated the glide slope alert envelope and is below 1,000 feet radio altitude.
Mode 5 provides protection for inadvertent descent below a glide slope while on an ILS approach. GPWS monitors the flight path in relation to the glide slope centerline while on the ILS final approach course. The Mode 5 glide slope alert is enabled when a nav receiver is tuned to an ILS frequency and receiving a glide slope signal, landing gear is down, and radar altitude is less than 1,000 feet. Should the aircraft descend below the glide slope to a 1.3 dot fly-up indication, the amber GPWS glide slope alert lamp will illuminate, and the voice message glide slope will be heard.
Glide slope.
Glide slope voice messages are initially softer and less frequent than other GPWS alerts and warnings, but become louder and more frequent as the aircraft deviation below glide slope worsens.
Glide slope.
Once a correction is made by the pilot and the aircraft is returning to the glide slope centerline, the amber glide slope alert lamp will extinguish and the glide slope voice alert will cease. To allow repositioning below glide slope when visual conditions are achieved, or on localizer-only approaches, pilots may elect to disable the Mode 5 glide slope alert function. This is done by depressing the amber glide slope alert lamp or switch either prior to or during a glide slope alert annunciation.
If the aircraft is more than 1.3 dots below the glide slope, the EGPWS issues a soft glide slope oral alert. This is called a soft alert. If the aircraft is below 300 feet radio altitude and more than 2 dots below the glide slope, the EGPWS issues a loud oral glide slope alert. This is called a hard alert. In both cases, the glide slope switch light illuminates amber. The repetition rate of the audio and the flashing light will increase as the radio altitude decreases and the deviation increases. Sub-mode 5 can be inhibited when the aircraft's radio altitude is less than 2,000 feet by pressing either glide slope switch light. When the aircraft radio altitude is greater than 2,000 feet, the glide slope warning is automatically rearmed. Modes 1 through 4 alerts have precedence over Mode 5 alerts. The EGPWS Mode 6 warning provides oral callouts below certain radio altitudes. The EGPWS will issue an oral minimums callout when the aircraft descends below the decision height. The decision height used by the system is selected by rotating the inner knob of the ADI decision height selector on the EFIS control panel.
Mode 6 contains altitude and bank angle callout functions designed to increase situational awareness for the flight crew. These callouts are selected by the customer when GPWS is initially installed in the aircraft. The decision height minimums callout is a function of radar altitude. The pilot sets the radar altitude bug or DH manually. and GPWS provides the call-out minimums at the selected altitude on the approach to landing.
Minimums.
Altitude callouts can be chosen from a large menu of possible combinations.
500.
These callouts are provided to pilots as a
300.
means to confirm aircraft position during approach.
100.
These callouts are just an example of one altitude callout menu. Bank angle callouts are designed to alert flight crews to the possibility of overbanking, which may lead to serious flight path deviation or loss of control. These callouts occur at preset maximum limits tailored to the aircraft type.
Bank angle. Bank angle.
Near the ground, radar altitude is used to advance the bank angle alert, so callouts are given sooner, providing additional time for pilot corrective action.
Bank angle.
A color weather radar is installed on the aircraft. Once operating, weather radar returns are displayed on the EHSIs when the EHSI is operated in the ARC mode. Weather returns are displayed in one of four colors depending on the intensity of the return. The weather radar provides a coverage of up to 300 nautical miles and will cover an arc of 45 degrees on each side of the aircraft. The radar can also be operated in the ground mapping mode. In this mode, ground returns are also displayed on the EHSIs. The radar system is powered by DC bus 1 and the 26 volts AC standby bus. The radar system consists of a weather radar control panel, a radar transmitter receiver, and an antenna located in the forward part of the fuselage. The radar receiver processes the radar returns and feeds them to the two symbol generators. The symbol generator units then display the radar returns on the associated EHSI. The weather radar system is controlled by the weather radar control panel. The operating mode is selected by the mode selector knob. The weather radar system is inoperative when the mode selector is in the off position. In this case, the weather message is displayed in amber on the EHSIs. The standby position powers up the radar system. However, in this mode, the antenna is not rotating and the weather radar transmitter is inhibited. In this mode, the word standby is displayed on the EHSIs. The radar will automatically return to the standby mode after the aircraft lands, even if the mode selector is in the weather position. The weather radar is operating when the mode selector knob is in the weather position. Weather radar returns are then displayed on the EHSIs when they are operating in the ARC mode. Radar returns are colored depending on the intensity of the return. Black simply means that no returns are detected. Returns in green indicate light precipitation. Returns in yellow indicate a moderate precipitation level. Red returns indicate strong precipitation. Magenta returns indicate intense precipitation. The radar system is placed in the ground mapping mode by placing the mode selector knob in the ground map position. In this mode, the color of the return varies according to the intensity of the return. When the mode selector knob is in the flight plan position, the radar returns are removed from the EHSI and the EHSI is placed in the flight plan mode. In this mode, target alerts can be displayed. When the target alert feature is activated, the EHSIs will display a green target message on the EHSIs. In the target alert mode, the radar will monitor an arc of plus or minus 7.5 degrees on each side of the aircraft. When the radar system detects a precipitation level 3 or greater, the target message on the EHSI turns amber to alert the crew. The test position of the mode selector tests the radar system and displays a test pattern on the EHSIs. The radar antenna tilt can be adjusted 15 degrees up or down by means of the tilt control knob. The range monitored by the radar is adjusted by means of the two push buttons marked by an up and down arrow. These push buttons can be used to select a range between 5 to 300 nautical miles. In the flight plan mode, Additional ranges between 500 and 1,000 nautical miles are also available. The gain control adjusts the sensitivity of the radar receiver. The gain control knob is a combination rotating knob and push-pull button. When the gain control knob is pressed, the radar gain is automatically set to a preset calibrated value. Once pressed in, the rotation of the knob will have no effect on the radar gain. When the gain control knob is pulled out, the gain of the radar system can be manually adjusted by rotating the knob to the desired position. When the gain is manually set, the EHSIs will display an amber variable message. A react mode compensates the radar returns for attenuation due to the radar signal traveling through precipitation. This presents a more accurate picture of what is happening behind a red zone. A cyan field on the radar indicates that no echoes are present behind a particular target. If precipitation is detected there, it will be presented as a target. These areas should be considered dangerous. The react mode is selected or deselected by pressing the react push button on the radar control panel. It is active in all ranges. When the unit is still in the warm-up mode, wait will appear on the EHSI. After that, weather react will appear in green. The react mode can be used at the same time as the ground clutter reduction feature. When both modes are in use, CR/R will appear in green on the EHSI. The radar antenna is automatically stabilized by the ATR system in order to provide a level sweep during maneuvers. This stabilization function can be turned on or off by the stab push button on the radar control panel. The target alert feature was discussed previously in this module. The target alert mode is selected on or off by the target push button on the radar control panel. When active, a target label will appear in green on the EHSI. Normally, the radar antenna sweeps the area in front of the aircraft 12 times per minute. Normally, the scan area spans an arc of 120 degrees. Recall, however, that the EHSI can only display an arc of 45 degrees. The scan speed can be increased by pressing the sect push button. This increases the scan rate to 24 sweeps per minute, but reduces the scanned arc to 60 degrees. Weather radar status indications are displayed on the EHSI. A green wait message indicates that the radar system is warming up. This message usually remains illuminated for 90 seconds. A green standby message indicates that the radar is in the standby mode. A green test message is displayed when the radar is in the test mode. A green weather message indicates that the radar is operating. An amber weather message indicates that the radar is selected on the EFIS control panel, but the radar is selected off on the radar control box, or the radar antenna is not scanning when the radar is selected on the EFIS control panel and the radar control box. A green ground map message is displayed when the ground mapping mode is selected. A green react message is displayed when the react mode is selected. A magenta TX is displayed when the radar is operating but the radar returns are dimmed. Some aircraft are equipped with a global positioning system, which uses a series of navigation satellites to provide position and altitude information. The standard GPS installation is the Bendix King KLN-90, which is discussed here. An updatable database contains information about airports, frequencies, VORs, NDBs, waypoints, SIDS, and stars. This database enables the GPS to provide the aircraft with lateral navigation capability. The information from the GPS is organized like a book. Information is organized by chapters, and within each chapter there are a series of pages. Some aircraft are equipped with a Global Navigation Satellite System, or GNSS, a more advanced GPS system. The HT-1000 model is discussed here. The GNSS system is capable of navigation functions such as Great Circle routes as well as standard GPS navigation. Refer to the HT-1000 Pilot's Guide for a detailed description of the system. The crew interacts with the GNSS through the Multifunction Control Display Unit, or MCDU. The MCDU is located on the center pedestal. The control panel includes a screen to display information as well as numerous push buttons used to interact with the system. The scratch pad is where the crew enters information into the MCDU. Scratch pad entries are made by the alphanumeric keys of the MCDU panel. Up to 24 characters can be entered into the scratch pad. The MCDU screen is divided into 4 distinct parts. There is a title field which displays a title related to the information displayed on the screen. Information is displayed in the left and right fields of the screen. Once information is entered into the scratch pad, it can be fed to the navigation system by means of the line select keys. These keys, located on either side of the MCDU screen, are used to assign a scratch pad entry to a particular navigation system value. Occasionally, the MCDU may display a message in the scratch pad. For example, if the crew attempts to enter an invalid value in a particular field of the screen, the MCDU will display a message to indicate that the data is invalid. MCDU messages can be cleared out of the scratch pad by means of the clear key. One press of this key will clear out the message. The clear key is also used to remove information entered by the crew. A single press of the clear key will clear out the last character of the scratch pad, whereas a continuous press of the clear key will clear out the entire scratch pad entry. The 7 keys located above the MCDU screen are used to access a specific chapter of the navigation system. These keys are used to access the route information, legs information, departure and arrival information, holding information, progress information, vertical nav information, and ATC information. Earlier it was mentioned that the navigation system information is organized like a book. Within each chapter of the book there may be more than one page of information to access. Since the screen is limited in size, these pages are displayed one at a time. The previous and next keys are used to turn the pages within the particular chapter. Lateral navigation information is displayed on the EHSIs. The EHSI can display waypoints, nearby VORs, airports, and ADF stations. This concludes the navigation module.